The point of this exercise 3.6.9 is that we must show why the LP norm for p not equal to 2 is not an inequality norm. So what should we be looking at? That's right, Caleb. Parallelogram inequality. Excellent job. So part A of this question is, before that, we're going to let our functions be these extremely complicated functions. F of x equals 1 plus x, g of x equals 1 minus x, and we're going to consider them on the interval negative 1 to 1. Okay. So part A is show that if we take the p norm and raise to the p power of either of these functions, we get 2 to the p plus 1 over p plus 1. And if we add them together, we get 2 to the p plus 1. If we subtract them, we get 2 to the p plus 1 divided by p plus 1. So let's see. We do need to do an integral or something. So let's see. That would be, let's just compute it, right? How about, it's actually always easiest to do the p norm to the p power, because then you don't have to put the 1 over p in there. So it's the integral of f to the p power. And this is from negative 1 to 1. So it's the integral from negative 1 to 1 of 1 plus x to the p power dx. All right. So let's see. Who knows what to do here? Right, Lucas. We can get rid of the parentheses because that's always greater than or equal to 0. So this is integral from negative 1 to 1 of 1 plus x to the p dx. And what can we do with that? That's right then, substitution. But I mean, we could just do it by inspection, right? This is just x plus 1 to the p plus 1 over p plus 1, negative 1 to 1. Right, and then you get 2 to the p plus 1 over p plus 1. Check. All right, now if we did the other one, let's see what would happen. Let's see if we do g p p. So that's the integral from negative 1 of absolute value of g to the p. So that equals integral negative 1 to 1 of absolute value of 1 minus x to the p dx. Now what would we do? That's right, Shaylin. 1 minus x is also positive on this interval. That is mighty convenient, isn't it? So let's see. So this is the integral negative 1 to 1 or 0, at 1. So we get 1 minus x to the p and dx. And let's see if we, so we raise it to the p power divided by that. We get p plus 1 divided by p plus 1. And let's see if this works. If I take the derivative of that, I get p plus 1 comes down. That to 1 less power p times negative 1. So in fact, I need a negative 1 out there. Good. And then I want to go between negative 1 and 1. And again, plug the numbers in. Get 2 to the p plus 1 over p plus 1. Check. Excellent. Now let's go on to the next step. We got to do adding the two functions together. All right, so let's do the adding the two functions together. So let's see, that would be the integral of absolute value of x plus g to the p from negative 1 to 1. So let's see, negative 1 to 1. Absolute value of f is 1 plus x. Plus g is 1 minus x. This is really going to be tough. Okay. Who knows what to do? Right, Peter. Excellent. It's negative 1 of 1 of 2 to the p dx. And so it's 2 times 2 to the p, because that's just a constant, and it's 2 to the p plus 1. Yay. Okay, now we have to subtract them. Let's see, so this one is, f is, negative 1 to 1. F to value of f minus g to the p power, so this is negative 1 to 1. F is 1 plus x minus 1 minus x, all to the p dx. And let's see, this is, I'm going to go negative 1 to 1. Absolute value of 1 cancel over, and get 2x to the p dx. Now what should we do? Right, Caleb, we got to divide it up because this isn't always positive, right? Good. So this is, so let's do negative 1 to 0, and then it'll be negative 2x in parentheses to the p dx plus the integral from 0 to 1 of positive 2x to the p dx. And so we get, pulling the 2 to the p's out. Yeah, I'm going to do that. Negative 1, 0 of negative x to p dx plus 0 to 1 of x p dx. And let's see what we get from that one. Antiderivative, right, Jalen, so that'll be negative x to the p plus 1 over p plus 1 times a negative 1. And let's see, and we go between negative 1 and 0 plus, right, x to the p plus 1 over p plus 1, going between 0 and 1. And we get 2 to the p, and so plugging in 0, we get 0, but then you get rid and plug in 1, so you get 1 over p plus 1 for that one. And let's see, this one you get plus 1 over p plus 1. And so the answer is 2 over p plus 1, so 2 to the p plus 1 over p plus 1. Check. And guess what? That's exactly what we were trying to prove. Fantastic. We want to show that for these two functions, then the parallelogram holds if and only if this equation, p plus 1 to the 2 over p power, it's supposed to be a power here, is equal to 3. All right, so let's check if that's true. Now, who remembers the parallelogram law? That is right, Caleb, right. It's the square of the diagonals, think of these as vectors, summed up, has to equal the sum of the squares of all the sides, and then the two opposite sides are congruent, so it's just 2 times one side length squared plus 2 times the other side length squared. Right, now we'll plug in the numbers we got for our particular functions from the last problem. And so let's plug those in. So f plus g, and these were all p norms, right? So we were calculating to the p power, so all of our numbers we're going to have to raise to the 2 over p. So let's see. So this one, let's see, I've got 2 to the p plus 1 raised to the 2 over p power, plus this one was 2 to the p plus 1 over p plus 1 raised to the 2 over p power, equals 2 times, and these were both the same, so let's just call it 4, and then this guy is 2 to the p plus 1 over p plus 1 raised to the 2 over p power. Right. Okay, so simplified, you have gives you that 2 to the 2 plus 2 over p plus, raise that to the power 2 to the 2 plus 2 over p plus 1 to the 2 over p equals 4 times 2 to the 2 plus 2 over p plus 1 to the 2 over p. And then let's bring that over there, and so we got 2 times 2 raised to the 2 plus 2 over p power is equal to 3 times 2 to the 2 plus 2 p power over p plus 1 to the 2 over p power. And see, those cancel, and you get 1. Put this over there. And this is true if and only if p plus 1 to the 2 over p equals 3. And let's see. Shadowline plugin 2. 3 to the excellent. All right, so the next question is, show that this number p plus 1 to the 2 over p is not equal to 3 for p not equal to 2. P greater than equal to 1. All right. Well, so this is pretty tricky. I think it might help if you graph it on the computer. Let's look at that. Desmos. Let's graph x plus 1. Okay, that's my p's, in other words. Raised to the, what is it, 2 divided by x. And for x plus 1 is the 2 over x. So look, it does only equal 3 here. So if we just show it strictly decreasing, then we're good. So let's consider g of x equal to x plus 1 to the 2 over x. Then for x greater than equal to 1. Then g prime of x is equal to 2 over, oh wait, well, you gotta rewrite it as e to the log of x plus 1 times 2 over x derivative. And then, let's see, it's the same thing, e to the log x plus 1 times 2 over x times the derivative of the inside. You got to use product rule, 1 over x plus 1 times 2 over x plus ln of x plus 1, and derivative of that be negative 2 over x squared. So simplified, this is equal to x plus 1 to the 2 over x power. That's where all that is, times, let's pull it an x out, and let's see, negative 2, right? And let's pull a 2 out. And then we've got 2 pulled out and over x pulled out. And so we got 1 over x plus 1 minus ln of x plus 1 over x. Right. And let's see. Is it obvious that this number, if x is greater than or equal to 1, that's bigger than or equal to 1. X, actually, for x greater than or equal to, well, as long as this is at least e. So let's say 2. And so then this would be negative, and then you can also check plugging in 1. It'd be 1/2 minus ln of 2 over 1. And that's 0.6 something, so yeah. So it's negative. So it's less than 0, so it's strictly decreasing. So therefore g of x equals 3 only at x equals 2. Excellent. And that shows you that the LP spaces for p not equal to 2 are not inequality spaces.